400 years ago, a French philosopher and mathematician invented a mathematical object so revolutionary that its impact continues to shape how we teach mathematics even today. This is a remarkable feat in a world where educational trends often shift in years, if not months. While, understandably, many students might rue the day that René Descartes introduced his coordinate plane, this elegant unification of algebra and geometry has become the backbone to secondary mathematics education in the United States. Hello and welcome. My name is Tim Raschuti, and I am dedicated to helping more people understand, enjoy, and love mathematics. By day, I'm an educator working for a classical Christian school in the Dallas area, but in addition to that work, I run several online channels on YouTube, on TikTok, and at my own website, which you can check out, polymathematic.net. My fascination and appreciation of the coordinate plane began in part because the school I work for does not have a high school. Our students usually graduate after 8th grade and move on to several different high schools in the area, all across the city. Because of this, I have very little direct knowledge of what they're going to experience in their high school career. I don't know the particular classes they're going to take. I don't always know the order in which they're going to take those classes. I don't know the teachers that they're going to take those classes from or what those teachers prefer to emphasize. When I prepare my students to leave my 8th grade algebra class, I make sure I'm equipping them with an idea big enough that not only will they be rewarded by repeatedly diving into this idea, it's an idea that I can be pretty sure will be explored universally. Regardless of the school, regardless of the class, regardless of the teacher, they are going to encounter this idea. And René Descartes' coordinate plane fits the bill perfectly. The coordinate plane, if it's been a while since you took a math class, is a simple yet powerful object. Imagine two number lines. One number line is situated left to right, as the classic number line typically is, and the other number line meets it perpendicularly, going up and down. The place where the two number lines meet is called the origin, and it, as well as any other point in the coordinate plane, can be represented by two numbers. The first number tells you your location with respect to that left-right number line, and we usually call it an x-coordinate, and the second number tells you your location with respect to the up and down number line, and we call that one the y-coordinate. Correspondingly, the left-right number line we actually give a name to, we call it the x-axis, and the up and down number line we call the y-axis. Fittingly, this ordered xy pair is what we call an ordered pair. And again, any location in the number line can be described by such an ordered pair. You would be forgiven for wondering what the big deal is about an idea so simple. But this is definitely a don't judge a book by its cover situation. The simplicity of the coordinate plane belies its extraordinary utility. Go back to that single number line for a moment. A number line is simple enough that we use it to teach children about counting and scale, even operations at some point. For example, as you shift values to the left or to the right, you symbolize addition or subtraction. You can even scale the number line by stretching it or compressing it in order to symbolize multiplication or division. However, it might be useful as you pile on more and more operations to think about this shifting and scaling number line in terms of a more stationary number line. So let's bring up a second number line here and visualize the connections between the two. We can now see them as paths from our starting values to their expanded or contracted values. Just this simple addition already begins opening up new horizons of understanding. Think about the classic result, a negative times a negative makes a positive. Have you ever wondered why it is that this is true? With the addition of this second number line, we can begin to develop a much more robust understanding of what multiplication is doing and why it must be the case that multiplying a negative number times another negative number makes a positive number. If we start with some large scalar, in this case, let's say that we're multiplying everything by 3, and we begin to make it smaller, we can see that second number line compressing. We eventually get to the special map representing multiplication by 1. That is, the multiplication that leaves every element in place from the original number line. But as we continue to make that scalar smaller, we can start to see the ways in which multiplication is connected to division. Scaling that first number line by a factor of 0.5 or 1/2 is the same thing as dividing all of the values by 2. If we push that even further, we can see the special property that multiplying by 0 has, as the entire number line collapses to a single point. This represents the idea that multiplying anything by 0 will give you back 0 in return. But if we push that even further, not just letting our scalars get smaller and smaller, not even letting them get fractional, but actually pushing them past 0, we can see this amazing thing happen. As we let that scalar pass 0 and go into the negatives, we see the entire second number line flip around. Multiplying these positive numbers on the right carries them over to the left. This is what it means to say that a positive number times a negative number yields a negative. But we can also see that what was originally on the left of our first number line now maps over to the right when we introduce this negative scalar. We can literally see why it must be that a negative number multiplied by another negative number makes for a positive result. Now, with operations this simple, the two number lines stacked on top of each other work well enough. Of course, if you imagine having to draw all of these little connections in yourself, you might be a little skeptical, but just given the visual, it definitely works. The problem is that if we introduce any operations even slightly more complex than merely addition and subtraction, multiplication and division, these connections quickly lose their coherence. It's much harder to see, for example, what's happening when we introduce just a simple scaling operation. The clean intuitive relationships we saw a moment ago become harder to discern and definitely harder to draw. For example, here's what the exponential operation would look like, here's what a root operation would look like, and here's what a trigonometric operation looks like. In all but the simplest cases, the visual representation quickly becomes quite cluttered. So here comes René Descartes. René Descartes' innovation is to place that second number line perpendicularly to the first number line. Going back to our visualization here, this is the result when we do that. All of a sudden, what was very difficult to discern earlier becomes much simpler to see. And again, this is going to be true in all of the operational cases where it wasn't true before. Our root curves make better sense now, our trigonometric curves make better sense now, our exponential curves make better sense now. Placing these two number lines perpendicularly to each other does a lot of the work for us to help us begin to understand what these operations are really doing. By assigning one axis to the values of that first number line, which we can now think of as input values, or what we sometimes call the independent variable, and then assigning the other axis to our output values, the values along that second number line also sometimes being the values denoted by our dependent variable, the variable that depends on the values of the independent variable. By doing that, Descartes creates a framework where abstract relationships can be seen as concrete shapes. Whether it's a straight line representing constant growth or a curve representing acceleration, the coordinate plane allows us to map, compare, and understand these transformations in a way that's intuitive and accessible. This elegant system doesn't just organize numbers, it makes mathematical relationships tangible, paving the way for a deeper exploration of both algebra and geometry. It is precisely this connection between algebra and geometry that not only gives the coordinate plane its enduring effectiveness, but also shows up as we think about how high school mathematics in the United States continues to be organized. To this day, mathematics in secondary education in the United States begins with the manipulation of algebraic expressions and equations, focusing especially on polynomials. Then we typically take what can feel like a detour into the world of geometry, seemingly leaving algebra behind for a time to focus on shapes and patterns and what we can prove, before we return to algebra basically to focus on functional analysis, lots of different families of functions situated within the coordinate plane. We usually reserve the simplest functions, called polynomials, for the study of Algebra 1, and then when we get to Algebra 2, often after geometry, we study those more complex families of functions. Finally, all of this is intended to culminate in calculus, where the geometrical insights of curves and the inherent infinite nature of geometrical objects is given rigorous mathematical grounding in limits, derivatives, and integrals, connected all through the coordinate plane. To better understand precisely how this particular tool, the coordinate plane, brings coherence to the high school mathematical program, allow me a brief digression into some mathematical history. For roughly the first 2,000 years of its existence, mathematics was geometry. If you were to speak to a Sumerian or Babylonian or Greek mathematician, first of all, that would be amazing. How did you learn all of those languages? But second of all, you would find that they were all geometers, the sorts of things that we usually associate first with mathematics, the sorts of things that we teach elementary school children, basic addition, subtraction, multiplication, etc., that wouldn't have even registered as the science of mathematics. That was some lower art reserved for merchants or bean counters. The peak of mathematical exploration was better understanding of shapes and relationships within figures. Then we do reach this period of time for roughly 1,000 years preceding Descartes, and Descartes, by the way, was born in 1596 and died in 1650. That's the roughly 400 years ago. So we're talking about from roughly 500 AD to about Descartes' time, we see a rise in a new mathematical science that today we would call algebra. Algebra, as it existed then, was the study of equations and their solutions. To be sure, the equations did not look like those that we study today. Instead of something like x plus 4 equals 10, which is called symbolic algebra, there would have been a sentence, a thing and 4 is 10. For a quadratic equation, instead of something like x squared plus 10x equals 39, you would have had a statement like a square and 10 of its roots make 39. And the expectation would have been to solve for the root, meaning the edge of the literal square. In that particular problem, however, you end up with two different solutions. Early on in the history of algebra, the negative solution would have been discarded as nonsensical. Algebra might have been stretching its wings, but geometry was still king, and the problem was understood fundamentally as a geometrical one. A square is an actual geometric shape with positive area and, for sure, positive side lengths. It's completely fine for the root, that is, the value of the variable in this case, to be something like positive 3, and for sure, 3 squared plus 10 times 3 does indeed make 39. But even though it certainly works numerically, it would not have made good sense in the hundreds of years preceding Descartes to say that the root could have been negative 13. Even though, again, if you actually work this out, negative 13 squared is 169, 10 times negative 13 is negative 130, and 169 plus negative 130 is still 39. It works numerically, but because it doesn't work geometrically, for the most part, we would have ignored that solution preceding Descartes' time. So on the one hand, you do have this burgeoning mathematical subject in algebra, but it's not really on equal footing with geometry, and it yearns to break free of its geometrical constraints. On the other hand, you can also begin solving problems from an entirely geometrical perspective and yet find its tools wanting. Consider a line. Actually, consider dozens of lines. For the primary tools of geometrical construction, the straight edge, that is the line, and the compass, a circle, for those purposes, any line is as good as any other line. What matters is what you can draw with them. But otherwise, lines are indistinguishable. Let's go back to just two lines for a second. The two lines pictured here are clearly not parallel. They intersect. But otherwise, there's no sense of place or orientation. There's nothing special about the location of the intersection. You might be able to say something about the angle between them, if perhaps the lines were situated in a triangle, for example, but otherwise you find yourself very limited. But it's here that the coordinate plane knits together algebraic and geometric understanding. It gives us additional tools to describe and clarify the relationships. If we situate these two lines in the coordinate plane, there's so much more we can begin to say about them. We can identify particular points on the line. We can use those points to describe where the lines start in some sense and how they proceed. We can describe that procession with slope, which is simply describing how the lines change up and down compared to how they change left to right. If we bring back a bunch of those original lines and we think about them now in terms of slope, we do get a distinction between some of them. We can sort them by positive slope, pictured here in blue, or negative slope, pictured in red. Or if we do go back to just these two lines and we define their slopes and we write their equations in terms of that slope and where the line starts, which we more commonly call the y-intercept, we get the origin of the dreaded slope-intercept form, or y equals mx plus b. We can take those points from earlier, negative 1 comma negative 5 for the blue line and 2 comma 1, and we can use a formula to compare the change in y to the change in x. This is what we call slope. We simply subtract the different coordinates, so negative 5, the first y coordinate on the blue line, minus 1, that second y coordinate, which is going to give us a result of negative 6, and then we're going to compare that to the horizontal change. Again, going back to an x coordinate now, negative 1, minus the other x coordinate of 2, which is negative 3. The ratio, negative 6 to negative 3, is 2, and so we would say the slope of this blue line is 2. For our red line, we might note points at negative 1.5, comma 4.5, and then another point here at 1, comma negative 3, and then using exactly the same process, subtracting y coordinates, 4.5 minus negative 3 makes 7.5, and negative 1.5 minus 1 makes negative 2.5, we get a ratio of 3 over negative 1 as we simplify this, or more simply, negative 3. Combining this with those location locations that the lines started, which we also call their y-intercepts, we get equations like y equals 2x minus 3, or y equals negative 3x plus 0, which we would more typically simply write as negative 3x. When Descartes situated geometrical figures, like lines and curves, in the coordinate plane, he gave us an entirely new valence with which to understand the figures. Equations can now be associated with figures. Certain curves correspond to certain kinds of equations. Consider the parabola. The parabola is the curve that corresponds to a quadratic equation, which we can say in general is equal to something x squared plus something x plus something. We give those somethings names, and then we alter those named parameters, typically a, b, and c. And as we do that, we can see the figure changing, shifting, and scaling in the coordinate plane. With the figure situated in the coordinate plane, we can now use the tools of algebra to better understand its behavior. Concomitantly, we can use the tools of geometry to better understand the quadratic equation associated with a given parabola. We can better understand why certain quadratic equations have two real solutions, some have just one, and others have none at all. We can better understand why the solutions are located where they are with respect to the axis of symmetry. It's this dance between algebra and geometry that we ask students to learn throughout high school mathematics, and that dance culminates in the ultimate combination of the tools of algebra and geometry: calculus. Descartes did not invent calculus. That would have to wait for his near contemporaries Newton and Leibniz. But it was his coordinate plane and the broader discipline of analytic geometry that laid the groundwork for its development. Calculus builds upon the coordinate plane's ability to visualize and analyze the behavior of functions. The two central ideas of calculus, the derivative and the integral, embody the interplay between algebraic precision and geometric intuition that Descartes' invention made possible. The derivative extends that concept of slope we were just looking at from algebra. On the coordinate plane, we understand slope as that rate of change between 2 points on a line, but calculus generalizes this idea to any curves. Essentially, what we want is an instantaneous rate of change, the slope of the curve at one particular point, which can be symbolized by a tangent line to that point. This allows us to describe how all kinds of things change, how quickly a car accelerates, how populations grow, how temperatures shift. The visual representation of the tangent line on the coordinate plane gives students a geometric anchor for understanding this abstract algebraic concept. The integral, meanwhile, tackles the problem of accumulation. What if instead of being interested in the rate of change at a particular point, we're interested in the area under the curve across some interval? Using the coordinate plane, we can visualize that area as the sum of infinitely many tiny rectangles. This geometric intuition guides the algebraic rigor of integration, enabling us to calculate areas, volumes, and total change. Whether we're measuring the amount of water filling a tank or the distance traveled by an object, the integral ties together the algebraic and geometric tools students have been mastering since their first introduction to the coordinate plane. In both of these cases, the coordinate plane is more than just a backdrop. It is the canvas that brings these ideas to life. By situating calculus within this framework, students are not only able to see the connections between algebra and geometry, but also gain the tools to apply these principles to real-world problems. As you imagine your student, and I don't know if you're the parent to a high school student or if you're a teacher of students, but as you imagine your students journeying through high school mathematics, it's easy to get bogged down in the particulars, factoring quadratics, proving triangles congruent, memorizing the chain rule. Those details are important, but they're stepping stones toward a bigger goal, teaching students how to think critically, connect ideas, and solve problems. Coordinate plane offers a horizon to focus on, a unifying structure that ties together what might otherwise feel like a series of disconnected topics. It's the thread that runs from simple number lines to the abstract heights of calculus, teaching students to see patterns, relationships, and the interplay between the abstract and the concrete. These skills extend far beyond the math classroom, equipping students to approach complex problems in science, technology, and everyday life. When you look at the coordinate plane, it's easy to see two simple perpendicular lines. But within this simplicity lies the power to describe and explore the world. This is what we're training students to do throughout high school mathematics. René Descartes' invention is a reminder that the greatest insights often emerge from simple, elegant ideas. It has shaped mathematics for centuries and continues to shape the way that we think about, teach, and understand mathematics. So, as your student navigates the details of their math education, help them to hold on to this bigger picture. Math is more than just rules and equations. It's a way of seeing the world, of making sense of complexity, and of discovering beauty in patterns and relationships. The coordinate plane stands as a symbol of that vision, inviting us all to explore the infinite possibilities it reveals. I hope that has been helpful for giving you a picture of what a student is likely to encounter throughout high school mathematics, this union between algebra and geometry that is ultimately explored in some form of calculus. Not every student gets through that entire path, not every student wants to go through that entire path, but when they are in the weeds, that is the bigger picture that you can help them hold on to. Like I said, my name is Tim Raschuti. I do this sort of thing at polymathematic.net as well as various social media outlets, YouTube, TikTok, and the like. If there's anything I can do to help you as you guide your student or students, please let me know, and otherwise I will see y'all around.